In our third problem, we are faced with a different situation. We can see that we know what my v function is, but my z function looks a little different. My v function is 2 times a quantity cubed, take away 7, but my z function is actually the inverse of v. So how do I figure out what the inverse of an entire function is? I remember from previous knowledge, I know how to find the inverse of multiplication, and I know how to identify the inverse of addition. So how do I find the inverse of a function when it's a bunch of different operations altogether? Well, that's actually what you do. You break the function down into the little operations that make it up. So the first part of my v function is actually that there's some quantity being cubed. It's the story of this equation. The second operation in my v function is that once I take that number and I cube it, I'm going to double it or multiply it by 2. Once I've cubed it, once I've doubled it after I cubed it, I'm going to take 7 away from that quantity. Well, that makes sense. A number cubed, then doubled, take away 7. The 3 steps of my function are written as 3 separate operations. So let's see if I can figure out what the pieces of those inverses are. The first inverse would be inverting a cube. How do I invert a cube? Well, I take a cube root. And I can write it with a radical notation, or I can write it as a rational in my exponent. I'm going to write it as a rational in the exponent, but I wanted you to see both ways. The second operation, doubling a quantity or multiplying it by 2, I can find the inverse of multiplying by 2 by multiplying by that inverse, which is a 1/2, 1/2 of x. And finally, the third one, the third inverse, would be instead of taking away 7, I'm going to add 7. So when I'm building this inverse to find whatever this z function is going to be, I start from my last operation and I'm going to build myself back up. So my z function, which I know is the inverse of v, I'm going to put all of these pieces of the operation back together. I'm going to start with my x plus 7. And then I'm going to half whatever my result would be. And then I'm going to cube root whatever that result would be. I'm working my way from in, moving out. So my z function is actually 1/2 of a quantity x plus 7 completely cube rooted. Another way to say that is 1/2 multiplied by a quantity x plus 7 completely raised to the 1/3 power. But the question remains is, how do I know that z of x is truly the inverse of my v function? I'd have to test it. And we recall from the previous video that if functions are truly inverse of each other, we can compose them within each, and we should be able to obtain the identity. That's the same rules that apply with multiplication and addition. We use the inverse to obtain the identity. So let's test it out. Our first one is we're going to take z of x and we're going to compose it within our function v of x. I'm going to take 1/2 times the quantity x plus 7, all raised to the 1/3 power. I'm going to cube that, then double it, then take away 7. If you can take a moment and just look at that expression, we can start to see with the knowledge that we're gaining over the past weeks that we see inverses peeking out through that entire expression. We follow the order of operations and we apply our exponents first. And we see that 1/3 and 3 are inverses of each other, so they create a 1. Anything raised to the first power is itself. So we rewrite the expression 2 times the quantity, 1/2 times the quantity x plus 7, all take away 7. We see that there's another inverse showing up in that expression where it's a 1 pair. 2 and 1/2 create the multiplicative identity. They create a 1 pair. They go away, and we can see now that we're left with quantity x plus 7, take away 7. There's another identity that's formed. This one's the additive identity. There's 7 zero pairs that are created, which leaves us with just the quantity x. So we can see from the composition of z of x within v of x that they are inverses of each other. But to be true mathematicians, we need to be sound and check v of x within z of x. Z of v of x. So we take our v of x function and compose it within our z of x. Wherever we originally saw our x, we're going to completely replace it with our v function. And working our way from inside out, following the order of operations, I see that there is now the additive identity. There are 7 zero pairs that were created. So it becomes 0 and drops away. We rewrite it as 1/2 times the quantity 2x cubed, all raised to the 1/3 power. I see that there is another identity. There's a 1 pair. 1/2 times 2 creates 1, and we're left with x cubed raised to the 1/3 power. 3, the power of 3 and the power of 1/3 are inverses of each other, and you can see that they cancel each other out, and we're left with x. So whether we have v of z of x or z of v of x, they both create the identity function. We use the inverse to obtain the identity. Pretty cool.